All right, so today I'll be talking about linear inverse problems. So here the goal is to try and recover structured objects with as few measurements as possible. So has anyone, can I get a show of hands, anyone seen any examples of linear inverse problems before? Like which? I'm not going to talk about compressed sensing. So I'm going to start off the bat with, I'm going to talk about linear inverse problems specifically motivated by some of the learning applications, where I think one of the interesting distinctions, I love compressed sensing, it's a great story, but I want to tell you about some of the other things beyond compressed sensing, where one of the distinctions is really that in compressed sensing, you get to choose what the sensing matrix is. So it's really this design versus passive distinction that you see a lot of times in the distinction between information theoretic problems and learning types of problems. So we'll see some examples of where this comes up. But one of the running themes and one of the most famous examples of a linear inverse problem beyond at least compressed sensing is the matrix completion problem, where this problem is motivated by problems in recommendation systems, and you can really think about it as trying to fill in large partially observed matrices from few observations. So I tried to avoid the usual compressed sensing because everyone knows that story by now. But unfortunately, whenever you give one of these talks, you're also compelled to talk about the Netflix problem and give that usual spiel, which I can probably do on autopilot now. So about 10 years ago, Netflix had a famous challenge where it was a little bit more of a publicity stunt than anything else, but the challenge was to try and improve upon their recommendation system in some quantitative metric in terms of root mean squared error. So you can think about the data that they released most naturally as being arranged as a very large partially observed matrix, where each row represents a different user and each column represents a different movie that they may or may not have rated. And each entry is just some numerical score from 1 to 5 stars about how much they liked the given movie. Now, to sort of mix it up, some things that were a little surprising to me when you actually look at this data set is it's not quite as big as you think. So it's about 500,000 different users and about 20,000 different movies. And of course, it's very natural to think about this as a really sparse matrix. After all, how many movies would you actually rate? It's actually not as sparse as you would think. So if you think about the density of how observed this matrix is, then you're really asking for a typical user of the about 20,000 movies that they could have rated, how many did they actually rate? And it's shockingly high. It's actually well above 1%. That's weird. I certainly haven't rated that many. This is on average, yeah. But this, of course, was actually cherry-picked to be the part of the overall matrix that was quite dense. So they actually selected only the users which had rated tons of movies and movies which had enough different ratings that you could actually say something meaningful about them. So in any case, the basic goal here is, can we approximately fill in the missing entries given a random number of its observations?
So you know this whole matrix, or you don't know the whole matrix?
So you know certainly the names of the rows and columns, but you only observe, let's say, 1% of its entries.
Oh, sorry, I didn't understand. So the 1% is how many? Because you're saying things that didn't rate are things that we had not observed.
Exactly. So the point is that if you could fill in the missing entries, then you have some good measure of, for a person who hasn't rated a movie, how much they might or might not like it. And the goal is to try and leverage your knowledge of other users who are potentially similar and whether or not they've rated the movie to get some baseline of how much even unobserved things a user might like a given movie. So your goal is to really be able to try and predict which things they'd like and suggest them to them. Now, here we can think about it as underneath this, there's this structured object, but what's important about it is the only hope of actually being able to fill it in is actually some notion of why it's well structured. So the usual assumption is that this underlying matrix, if I could coerce everyone into rating every single movie, then the hope is that this underlying matrix that I have partial access to is approximately low rank. Now, this is an important thing to try and pull apart and understand why it might be approximately low rank. And I think the best motivation is that if you took this matrix and you just literally wrote it out what it meant for it to be approximately low rank, approximately the sum of not too many rank 1 matrices, what could you imagine these rank 1 matrices as being? So one thing, for example, is these matrices could represent some notion of categories. So if you think about a category like drama, then you have this rank 1 matrix potentially that represents, it's an outer product of 2 vectors. So the first column here has an entry for every different user, and the outer product of another vector that has an entry for each different movie. And the actual numerical values represent some intensities. So you can think about it as, how much would a given user be interested in drama movies? And for a given movie, how much would that movie appeal to someone who's potentially interested in drama? So you could choose any categorizations if you want, but this is the basic mechanism by which you could imagine it being somewhat low rank. So you could also hope that another one of the categories is something like comedy. Again, the entries in these 2 vectors represent intensities, and things like sports, or you could have finer granularity than just this. And the usual assumption, which is usually an assumption you make just for simplicity, and many of the results that I say will actually generalize beyond this setting, but the usual assumption for simplicity is that the observations you're given are uniformly at random. So this would correspond to actually people rating random movies. It's true that what you really need is that you need enough randomness that people have rated many different things, but I can tell you more about that later, and I don't want to get too bogged down in the modeling details at this point. But the basic idea is that with this type of setup, if you have some structured object, in this case an approximately low rank matrix sitting underneath, can you really recover it from a few random observations? And actually conflated within this is both an algorithmic and a statistical question. The statistical question is how many observations would you need? And the algorithmic question is, can you really hope to do this with efficient algorithms? So, the same way that you can see a kind of parallel story for those of you who've seen compressed sensing, there's a very parallel story with matrix completion. Because the same way that in compressed sensing that there's a natural non-convex optimization problem you could try and solve, so too for matrix completion there's a very natural non-convex first try. So if I were given random observations from this, let's say even low rank matrix to keep things simple, one natural thing I could try is I could look for some way to fill it in. So my observations are the set omega, and I observe Mij at the pairs in omega. And I could look for an x that agrees with my observations so far. And among all such x's, I want to find the one with smallest rank. That's a very reasonable thing to do. This, of course, looks hopelessly non-convex and NP-hard. Because taking 2 matrices and averaging their rank doesn't produce something of at most that rank, so it's very non-convex. But the saving grace is that for matrix completion and actually for a huge scope of other linear inverse problems, there are very powerful, shockingly powerful convex relaxations that are almost as good as the non-convex problem that you first started with. So I want to explain what this convex relaxation is. So here's what you do. This is an attempt to define another convex program. And how I'm going to define this convex program depends on what's called the singular value decomposition. So imagine I give you some matrix X, and this is your hypothesis. Originally, you want X to agree with M on the observations so far, but you also want some norm to tell you which X's are better than which other ones. We started off with the rank as some sort of metric for how good the X is. Let me define a different one. So you take X, this hypothesis, and the singular value decomposition, which is one of the most powerful tools in linear algebra, tells you that you can always write any such X in the following form. You can write it as the product of U times sigma times V transpose, where U is an orthogonal matrix, V is an orthogonal matrix, and sigma is a diagonal matrix, which the entries are non-negative and are called the singular values. Now, the important thing about why this decomposition shows up all over the place is because from it, you can just readily read off a lot of the properties about the matrix that you care about. It just becomes readily apparent because, for example, the number of non-zero singular values is exactly the rank. So if I start off with, I think about the entries along the diagonal, the L0 norm, the number of non-zeros is the rank. And the same way in compressed sensing, you start off with an L0 relaxation, that's L0 optimization problem, that's hard. Well, you could instead use the L1 approximation to it, which in this case is exactly the nuclear norm. So instead of caring about the number of non-zero singular values, which is the rank that would lead to the non-convex problem, you instead look at the sum of those non-negative values. That itself is a norm called the nuclear norm. Actually, I'm not sure why it's called the nuclear norm. If anyone knows, I'd be curious, but that's what it is. And this leads to a very natural relaxation then. It was first introduced in a really beautiful PhD thesis of Maryam Faisal. And what she studied was this convex program. So you look for the x that agrees with your observations so far, and among all x's, you choose the one that has the smallest possible nuclear norm. That's the exact parallel story to what happens in compressed sensing. So in fact, Faisal only showed that it worked empirically and that it worked really well empirically. But it wasn't until later that we actually started to get a theoretical handle on why it actually works. So there's a beautiful work that is almost entirely forgotten, this work of Cerebro-Schreibman, which actually gives some really interesting tools for understanding the nuclear norm. I'm going to come back to that and tell you more about it because I love that work. Then after that, there was some work of Recht, Faisal, and Perillo, which showed, for example, that for a related problem called matrix sensing, that such convex programs are a good idea. And it wasn't until Candice and Recht and later work that people were actually able to show powerful theorems for matrix completion itself. So one example, there are actually probably a few thousand papers on this topic by now, but one nice theorem that comes from Candice and Tao, which is fairly representative, is the following thing. Imagine M is exactly low rank, right? So it's rank R, and it's an n by n matrix. Then there's also some notion of what's called incoherence. So incoherence, what it really means is that, remember, you're given random observations from this matrix, but if the entries in this matrix were really concentrated in just a few locations. Imagine M was a rank R matrix with only entries along the diagonal, and R of them. You just have no hope of actually seeing those entries. So incoherence, what it actually means is that you need the entries to be spread out so that a typical sample sees them. Or more precisely, you need that the singular values of M are not aligned with the standard basis. In any case, you can ignore that because, if you know what I mean, then that's great. But if not, incoherence is a very natural condition. What they showed is that under these conditions, then this convex program, which you can obviously solve in polynomial time, actually recovers M exactly from n times R times log squared n observations. This is amazing, right? I mean, this is amazing because just the...
Means that it's non-sparse?
Yeah, exactly. So C incoherent, there's a few ways people define incoherence, but here I'm saying that, let's say you need each of the entries to be, if you think about a typical singular value, if it were random, then its entries would be about, poly log n divided by root n. C is, the extra, and the smallest they could be is 1 over root n. So C incoherence means they're at most C over root n. So you could think about C as being a constant or poly log n worst case. But, what's amazing about this thing, I just want to emphasize this, to underscore this, is, how many parameters define the model to begin with? It's a rank R matrix. So that means it has a decomposition as an n by R matrix times an R by n matrix. So the total number of parameters that define it is 2 times n times R. So the number of observations that you use in here is a poly log n factor larger than the number of parameters that define the model, and yet you're actually able to recover it exactly. Now, what's kind of amazing here is the fact that there are two.
Actually a lower bound because of the other assumption.
That's right. Yeah. So you need at least n times r observations in an algebraic sense, because that's how many real parameters you have. So one.
Somehow redundant also.
No.
Rotation, like you said.
Yeah, that's right. So what you would really do is up to the rotations, only subtract off lower order r by r degeneracies. So there's actually a lower bound which for r that's smaller than n, you really do need omega of n times r, but that's a good point. You just have to mod out by that algebraic indeterminates. Was there one more question?
Is there also some way of understanding like lower bounds and C on dependence in C?
Okay, so that's a very interesting technical question. The worst thing about this is probably the dependence on the incoherence. There's a lot of work on that, but I don't have too much to say about it because I'm not sure we've really gotten to a reasonable understanding, except to say that it's clearly still an important question. Now, in fact, I actually want to emphasize one more thing, which is that, what's conflated in here are two issues, right? So first is the information theoretic thing. This theorem already tells you an information theoretic thing, that it's not obvious that you can recover these things information theoretically, regardless of your algorithm, with a polylog n factor larger number of observations compared to the number of parameters that define the thing, let alone the fact that there's an actual algorithm that actually meets that information theoretic bound roughly. That's pretty cool. There's a lot more work on matrix completion. One of the things which people really love to study is how to do the similar things without solving a convex program like this. So one thing that you can do is there are actually things that were at first thought just to be heuristics called alternating minimization, that iteratively they just go back and forth trying to solve a non-convex problem, fixing one side and optimizing over the other. Yet you really can analyze these heuristics and show that they really do work. And by now we know that they get somewhat similar guarantees, at least in terms of the dependence on n and r. There are issues that extra parameters creep up there, things like the condition number that don't naturally show up in the convex program. But what's amazing about those things is that they're much faster and much more space efficient. You don't even have to write down the n by n matrix because they do it implicitly in the factorized space, which is cool. I'm going to give you...
Popular practical solution.
That's the most popular practical solution. One should be careful that there really are guarantees that the convex program has that this does not have. So one of my favorite things to do these days, because I like toying with these models, is there's something within theoretical computer science called semi-random models, where the idea is sometimes you can mess up algorithms by trying to make their lives easier. So imagine we're given random observations of the matrix, but an adversary comes along and reveals more entries to you. Nuclear norm minimization clearly continues to work because it's just more constraints, but alternating minimization actually fails. So that's actually kind of a strange thing. So not sure people have really talked about that one. I'm going to quickly tell you at a high level about where some of the other threads go for linear inverse problems. There's a lot more you can do. One of my other favorites is robust PCA, which is going to sound a bit similar, and I'll just describe it at a high level to keep things not too bogged down. So the idea is, in matrix completion, we were given sparse observations of a low-rank matrix. A completely different line of questions is, what if there was an underlying low-rank matrix, you observe everything, but some random fraction, like a constant fraction of its entries, were completely corrupted by an adversary, and you have no idea which one is which. See, if you knew which ones were which, you could just ignore them, and you'd be stuck with an ultra-simple matrix completion problem, because you've actually observed many more entries than the things that you haven't observed. But here the issue is that you don't actually know where these sparse corruptions are. There's actually a different convex program that works, and the idea is kind of a hybrid of two different things, where you try and minimize the nuclear norm of some x, so you're given m, and you try and write it as x plus s, where you want x to be the low rank part, and you want s to be the set of sparse corruptions. And what you do is you use the nuclear norm to induce the fact that x is low rank, and you use an L1 norm on s to induce the fact that it should have sparse entries. And this really does work. So it turns out that you can separate low rank and sparse components even with nearly linear rank and a nearly quadratic number of corruptions, which is cool.
So the goal here is to estimate x or the x plus s?
The goal, well, they're the same thing, because if you get x, you get s. So it's really to denoise the corruptions. In fact, one of the ways that people use it is the way that they apply it is they actually take image data. And you can imagine you have some security camera which has some background that's pretty fixed. And I guess you assume the background is a low rank matrix. It's kind of weird that this works. And you think of the people as being noise. But it turns out that you can actually use this convex program to separate the people from the background noise, except for that one guy who's just standing around there talking on his cell phone, I think. But this is what people apply it for, even though it looks quite a bit different than the original problem. There's one more that I can tell you about, which I'm going to tell you at a similarly high level before I tell you about some other things. So there's also this problem called super resolution that's actually related to compressed sensing, except for the fact that you don't have discrete locations. So here the idea is, imagine you have some set of points that you're measuring through some optical device. Now the idea is that these points, a first cut approximation is that, so there certainly are not too many of them. And the compressed sensing approximation would be that they happen at grid points and at discrete locations. But the compressed sensing off the grid and super resolution style assumptions don't make any assumption. These are actually at real locations. And the question is, with only low frequency measurements, can you actually recover them? And they're actually similar convex programs that, again, you're given linear functions of some structured underlying objects, and they're convex programs that do interesting things. So I can tell you more about that offline. All right, but what I really want to do is I want to tell you about a sort of different take on some of these things, which, what was kind of miraculous about some of the things that I described so far is that there were no computational obstructions to actually doing these things. So you did as well as you could hope for in all of the settings, but there are other linear inverse problems which people have spent a lot of time thinking about and are stuck. And those are actually very interesting candidates for where computation actually has a non-trivial role to play in that you can't do everything you want, but they're actually interesting trade-offs. So I'm actually going to talk about a generalization of matrix completion to tensors, because we talked about tensors yesterday. So it's a good opportunity to sort of take a different look at something else non-trivial you can do with tensors. And actually, these are the only two non-trivial things I know how to do with tensors, are Ingenerate Algorithm and what I'm about to tell you. So, before I work up to that, so instead of just jumping into can you find low-rank tensors given few observations, why would you want tensors to begin with? So let me actually consider a different recommendation problem, because what I claim is that this Netflix problem is a setting where each of your observations is defined by two attributes. It has a numerical score, but the two attributes are a person and a movie. But there are a lot of settings where actually thinking about it as only two attributes has already given up a huge part of the game. So I don't know if you guys are familiar with Groupon, but that's another recommendation problem where the goal is to try and recommend activities to different users, things like, ski trips or, restaurant deals, which you would go in groups, that kind of thing. But the idea is that fundamentally you could think about this as a matrix problem. Underneath it is some sort of preference on how each different user would like each different activity. But what I claim is there's actually a missing dimension to this that's really critically important, right? So time. If you think about something like a ski weekend, of course, I live in Boston, so you can recommend skiing year-round because it always snows. But I'm told there are parts of the country where sometimes it doesn't snow, and you wouldn't want to recommend skiing. The basic idea is that you can think about all of those activities, how much people like them or how much you want to recommend them, actually has a big time-like component, right? It could be season, whether it makes sense to ski in the summer or not. But it also could be, is it a weekend, weekday? Is it an evening activity? Does it need to be a long weekend? You could think about all sorts of things, or any possible combination of them. And that gives us a different dimension. And the same way we can think about our actual observations as coming from a third-order tensor, whatever you want, but the fact that it should have a somewhat low-rank structure owes to the same types of thought experiments as before. You know, one of the categories could be something like snow sports or other sorts of time-dependent activities, where now you have the outer product between 3 different vectors, one of which has an entry for each user, one of which has an entry for each activity, and one of which has an entry for each different time period. And the entry in that vector is then just some intensity of, you know, how much is this user interested in snow sports, how much does this activity appeal to someone interested in snow sports, and how much is this time period appropriate to actually make to recommend snow sports to someone. So the same type of thing is actually going on underneath, and you could assume, let's say, that we have access to an approximately low-rank tensor T. Most of it I'll talk about is exactly low-rank, but the things I say will generalize. That's actually why I like the Cerebro-Schreibman types of work much better than some of the exact matrix completion things, because those are very beautiful and elegant, but they don't work very well with noise, whereas Cerebro-Schreibman is actually easier, as we'll see, and works with noise. So the basic idea is, we can ask the same question, right? We have a structured object which we're getting passive linear observations from. Can we approximately fill in the missing entries given few observations? So, more attributes in general for, learning problems, they lead to better recommendations and better predictions you make, but fundamentally more complex objects. So as soon as you venture out into the jungle, you're more likely to get into computational impediments, which is what's going to happen here. But there'll be something interesting. So I've already told you about some of the troubles with tensors. There's another trouble. So here's what you could try and do, and people tried to do this for a while. Well, the nuclear norm worked for a matrix, so let's try and use it for a tensor, right? So we can look at minimizing the nuclear norm of a tensor such that it agrees with the observations we have so far. I haven't really defined what the tensor nuclear norm is, but it's a pretty simple thing where you're really asking, if you look at the convex hull of some rank 1 tensors, how close can you be into that convex hull? How much do you need to dilate it? So actually, this is a convex optimization problem. This is a norm, the tensor nuclear norm. But the trouble is that not all norms are good. That's something I think people forget. This norm is bad. It's actually NP hard to compute. It's actually connected to quantum information theory, which is where it comes up in a very different context, because this norm is often used as a way to guide the fact that 2 different states are unentangled. But it was actually in this literature that you can retranslate the results and say that it's NP hard. And, as I already told you, if you try and generalize things for matrices, you're going to have a bad time because of the usual list. But, let me start with something naive first, right? So in Ingenerate's algorithm, if you remember from last time, I told you how tensors help solve the rotation problem because of this uniqueness issue that you can't find the factors uniquely from just the matrix. But at the end of the day, there was something a little suspicious there, because it's not clear we really used tensor structure as much as the fact that we had 2 different matrices that were interrelated, because ultimately we just did something to the tensor to turn it into a matrix. Let's try and do the same thing. Your first cut for can you deal with tensors is to close your eyes and pretend they're not tensors and they're just matrices. So what could we do if we just wanted to pretend tensors were matrices? So there are kind of 2 trivial things which are really the same thing. So one thing we could do, actually one thing we could do is we could take this tensor, which is, n1 by n2 by n3, and we could flatten it into a matrix so that it's n2 times n3 by n1. So you're taking this triple of indices that index the tensor, and you're mating 2 of them and treating it as a meta-index that indexes the columns instead. And that's how you get this dimensionality n2 by n3. So what you're literally doing is you're saying, I want to make recommendations by thinking about each pair of activity and time as a completely different object, so that I don't learn anything from the fact that it's the same activity across different times, or same time with different activities. And you're just rearranging the entries of this tensor. Now, it's actually not hard to see that this rearrangement is something which doesn't increase the rank. Because, the usual trick, all you can do with tensors to understand what they're doing, is you think about what they're doing on a rank 1 object, and then you extend it just through multilinearity. So what would it do on a rank 1 tensor is you would end up with a rank 1 matrix, which instead would, being the outer product between A, B, and C, would be the outer product between A, and then some new longer vector that depends on both B and C. Literally what you're doing is you're taking B and C, B times C transpose, and taking that matrix and flattening it to create a longer vector, and that's the thing you take the outer product with A. Now that's exactly what you do on each of the rank 1 terms, so this is actually a proof that the resulting matrix is approximately low rank. But now you're going to have a bad time because, how many observations would you need? The issue is that this matrix is highly asymmetric. Let's say n1 equals n2 equals n3 equals n, but just to keep the discussion simple. Well, then the issue is that one of the dimensions of this is n squared length. So the number of parameters that define the model is no longer n times r, but n squared times r. So you'd need n squared times r observations, which is way more than the number of parameters in the approximately low rank tensor. This is actually literally the same strategy as taking the tensor and completing it slice by slice for each of the matrices. That for the first one I'd need n times r, for the second one I need n times r, and all the way through I'd need n squared times r, because I'm not treating a tensor as anything different than a stacked collection of low rank matrices that have nothing to do with each other. So the basic question is there anything you can do to leverage the structure across the slices in the tensor? And amazingly, there's a couple hundred papers on this, and they suggest really fancy norms, but they don't actually get better guarantees than n squared times r. So the question is, can you beat flattening? And what I'll tell you is you can, but you can't get all the way down to the information theoretic threshold. So that's what I find exciting, is that there actually is a genuinely different way that computation interacts with the statistical and information theoretic question here, that you can't get all the way down without doing some pretty shocking things in complexity, but that there still are non-trivial algorithms. It'd be pretty boring if every time computation plus statistics meant either or. Like either you could ignore it and you can always reach the information theoretic limit, which is what people like to believe, or if when computational intractability plays a role, it just means you're stuck with the trivial algorithm. But I think it's cool when there's actually something non-trivial. So what I'm going to do is I'm going to tell you a corollary of our results that's a little bit easier to parse, and then I'm not going to tell you how we prove it. Instead, I'm going to give you a reinterpretation of the matrix completion case that explains how it's connected to random CSPs, and then gives you some foreshadowing of where these things come from. But let me consider a simplified setting. So, imagine you have these vectors, AI, you have AI, BI, CI, and now you need something to sort of bring you out of some weird pathological things. So what I'm going to assume is that there's some random variable that scales how you add up the rank 1 terms, that it's not pathological. I'm going to pretend it's a Gaussian, but it could be any diffuse random variable that has some anti-concentration that you want, and it'll have some additive noise. So here's the main result, right? So because this random variable, which governs how you're adding things up, well, it's a random variable, that means the entries of T are themselves dependent random variables. Now, if you think about the typical case, A might be a vector with entries between 1 and -1, same with B and C, then you would hope that in each of the entries in this tensor, you're adding up R variables which have some, constant kind of variance to them. So the point is that if you assume any lower bound of the variance, in fact, this is probably a typo, you need variance at least R over polylog n, then what's true is that there's an efficient algorithm that given n to the 3/2 times R observations outputs a hypothesis X that for almost all of the entries gets them almost entirely correctly. So for 1 minus little o of 1 fraction of the entries of T, X is multiplicatively close within a 1 plus or minus little o of 1 factor of T. So the important thing is that it's n to the 3/2 times R and not n squared. And let me just digest this, right? So these variance bounds, all you're really assuming is that the...
And what is that here? The number of the
Yes, it's the size of omega, exactly. M random observations, uniformly random. So I really should have written variance of T is Tijk for is at least R over poly log n. So it's something like 1 over poly log n, so it's as n increases, but it is something that doesn't go down as sharply as one would like.
And for the little over one fraction of the entries where you don't have this guarantee, like can you control the overall norm?
No, because I will only assume those could be pretty arbitrary noise entries. So what's bad about this is that when the noise is 0, it doesn't degenerate to exact completion. That's something that people really like for matrix completion, although I'm not sure that it's the right compromise, because those things tend to be less noise tolerant. Here you actually lose something that just depends on your average noise, which is, it follows from the Cerebro-Schreibman types of things. I'll explain a little bit more about that later. But the main thing is, I mean, you really just need that the AIs, BIs, and CIs are diffuse, that they have spread out entries so that they're not too concentrated. So it's some kind of generalization of incoherence. But here's something really bizarre about this, just to put this in the context of last time. So you remember one of my open questions was, can you decompose tensors, third order, when you have R is n plus log star n? That was the open question. Forget even 1.1 times n, right? This actually, you can think about R as being small if you'd like, but something weird happens is I could consider R to be large if I want to too. So if I plug in R as n to the 3 halves minus delta, way, way, way larger than n, that's called the overcomplete case. Well then my m is still n to the 3 minus delta. So I'm still observing a sub-polynomial fraction of the entries of the tensor, and yet I'm able to complete it, even in a highly overcomplete case. So we can complete tensors from a sub-polynomial fraction of their entries, even in settings where we can't decompose them, which is bizarre, even if I gave you the entire tensor. So that's really strange, I think, because it means it's something that all-chain minimization, as far as we know, can't do, because all-chain minimization would actually find the decomposition in addition to completing it. Okay, and then I'll tell you a little bit about lower bounds. So not only is this tensor nuclear norm hard to compute, it's even hard in an average case sense I'm going to say this very vaguely. It turns out that there are certain frameworks for proving tensor prediction, which a lot of these things fit into, which if you could solve tensor prediction with M observations, then there's a very simplified case of even just a noisy rank 1 tensor, that then the things that you could do would immediately imply that you could refute random CSPs, things like 3 XOR and 3 SAT with M clauses. But this is something that we study in theory, that even though when you take a random 3 SAT clause like n log n clauses, information theoretically it's unsatisfiable and really far from being satisfiable. It's something that we don't know how to algorithmically prove is true and certify through like a convex program, even when you go all the way up to n to the 3 halves. So we know even lower bounds against very powerful families of semi-definite hierarchies. And what that means is that you actually can't beat this strange little n to the 3 halves times r within things like the SOS hierarchy. So, and actually if you could, you would solve this, average case conjectured hard problem. So it's something where there actually is a complexity theoretic obstruction to getting all the way down. All right, so those are things I'm not going to tell you about because I've given this talk a few times and I've given up trying to do it. It's not hard, but it involves a lot of baggage between learning the names from different things because it's about connecting 2 different areas. So what I'm going to do is I'm going to forget tensors and I'm going to tell you about the connection. Let's just consider matrices, and I want to tell you about a reinterpretation of matrix completion that makes it a bit clearer why 2 different communities are actually studying the same problem. And that's all I want to tell you. All right, so let me even do a much simpler case study, simpler example, right? Forget matrix completion. Let me give you the following even simpler problem, right? Which you clearly have to be able to do if you can do something interesting. Can you distinguish between, a hypothesis testing problem, whether it's low rank, but a little bit noisy, or complete random garbage, right? So case 1 is approximately low rank. Imagine the underlying matrix was rank 1 plus noise, okay? So each of the entries, think about the entries in A, this underlying vector, as being plus minus 1s. And you have AI times AI transpose. That's a plus minus 1 rank 1 matrix. Now, the slight complication is that maybe a quarter of your entries are not actually from this rank 1 piece, but are random plus minus 1s. So in this setting, there is some low rank structure. In fact, there's some rank 1 structure that if you learned that rank 1 structure, you could certainly predict the entries non-trivially for M, because you would certainly get at least 3/4 the entries right. Actually, you'd get 7/8. Or can you distinguish it from the case where your observations don't come from a rank 1 piece, but are just complete noise? Every entry is a random plus minus 1. So this is a very natural distinguishing problem, which I claim that matrix completion has to solve, at least noisy matrix completion. Case 1 is something where the entries are somewhat predictable, and case 2 is something where they're not. So when you run algorithms in general, what they output will tell you a little bit more. It'll give you not just the hypothesis, but a lot of times a baseline about whether you should hope for good predictions or not. And those types of things actually solve this distinguishing problem. That's why this problem you can actually reformulate the results in matrix completion as giving algorithms for the simpler problem, and they're easier to state that way. But you could also tilt your head and think about this as a problem involving random CSPs. This is the intersection point between these two different communities, is that actually here's a reinterpretation. Imagine we were in case 1, where we really did have this planted approximately rank 1 structure. Now, each of my observations is a pair, ij, along with an entry plus minus 1. Now, I could tilt my head and think about each of those observations as being a clause, a 2 XOR clause, because what's really going on is that entry ij, which is populated with the sign sigma, well, that's the same thing as taking variables vi and vj and constraining their product to be equal to sigma, where the variables then take on values plus minus 1. When you actually when you find a rank 1 piece that agrees with a lot of the entries of M, that's literally finding some of those settings of the variables that agrees with these clauses, right? And you can actually do the mapping the other direction too, that a random 2 XOR formula with a planted somewhat good solution is actually literally case 1, and a random 2 XOR with no solution whatsoever is literally case 2. So this is actually the common language that you can go back and forth between these problems. And there's a problem that's studied within theory called strong refutation. So now I'm going to make a little bit more precise what I mean by refutation, is that we're going to say that an algorithm strongly refutes random 2 XOR with M clauses if the following is true. If you give me any 2 XOR formula, psi, then my algorithm is going to output a quantity value. So it takes the formula and computes something, and it has the property that value of psi is always an upper bound for opt of psi, the largest fraction of clauses you can satisfy in that. So you always want that your algorithm outputs a fair upper bound that, it says you can only satisfy 3/4, you certainly can't satisfy more than that. So there's the largest fraction of clauses that can be satisfied. But you also want the property that with high probability it works for a random formula. That when you choose a random formula with M clauses, with high probability the algorithm outputs a value that's half plus little o of 1. So this is an algorithm that we all know that a random 2 XOR formula with enough clauses n log n will be really far from satisfiable, that you can only get about half of its clauses right. What this is asking is there an algorithm to certify that fact that doesn't cheat? So condition 1 prevents you from closing your eyes and saying half plus little o of 1, because you have to be fair on everything. And constraint 2 prevents you from just saying 1 all the time, because you actually want it to be good. So within 2 XOR types of things, we have great algorithms for refuting, strongly refuting random 2 XOR. But once you go to third order CSPs like 3 XOR or 3 SAT, then these problems become hard. Even though information theoretically you can do them with n log n, we don't know algorithms that work all the way down to that, and it's conjectured that you can't. So now let me actually tell you the one lemma whose proof is so short that I will still have half of the slide remaining. So it is a very short lemma, incredibly short proof, but this is the crucial thing that relates the two. So the idea is that if you now have this language, this dictionary, between matrix completion and random CSPs, let's leverage it for something. Let's say how one thing says something about the other. So if I take my random observations and think about them as being associated with some random 2XOR formula using the mapping that I told you, where each entry ij with sigma goes to a clause corresponding to it, let me call that matrix A. So this is a sparse matrix with plus minus 1 entries. What I claim is the following. Remember, opt of psi is the largest fraction of clauses you can satisfy in phi. I claim there's a relation between opt of phi and the spectral norm of A. Right? So one way to think about this is just that, the left-hand side, imagine opt of psi was 1, right? So the left-hand side would be 2 minus 1 over n is 1 over n. So what I'm really saying is that if it's perfectly satisfiable, I better be able to create a quadratic form on A that's large, and that proves a lower bound for its operator norm. All I would do is I would literally take my satisfying assignment, and I would map it to a vector, which if the variable was plus 1, I'd map it to an entry with plus 1 over root n. And if it was minus 1, I'd map it to minus 1 over root n. The root n is just to normalize it to be a unit vector. Now, when you take that quadratic form on A, every one of your entries you agree with because it's satisfiable. So you pick up a 1 over n factor because you're multiplying 2 root n's in the denominator. And you pick it up m times because that's the number of observations. So when I divide by m on the right-hand side, I would exactly get the corresponding 1 over n. So if I had a perfectly good satisfying assignment, that's a lower bound on the operator norm. Even if I had a pretty good assignment, it would still be a lower bound on the operator norm. But the important thing is that now you can just appeal to random matrix theory. So a random matrix with m observations has operator norm about square root of m over n. And what that means then is if you plug in that side, you get square root of 1 over mn on the right-hand side. That's little o of 1 once m is little omega of n. Once m is n log n, you're in great shape because if the right-hand side is little o of 1 over n, the only way that could be true is if opt of phi is half plus little o of 1, and you've just certified that the formula is actually not satisfiable. So a spectral bound immediately implies strong refutation. That's actually the same spectral bound that allows you to distinguish between case 1 and case 2. Actually, that distinguishing problem is really trivial because in the planked case, there'll be a large spectral norm, and in the random case, there won't be. Same spectral norm underneath it. In fact, it's the same spectral norm that allows you to prove that matrix completion works and that nuclear norm is a good idea. And now I can finally return to Cerebro-Schreidman, and you'll see why I have given up talking about the tensor completion case, is because now I have to introduce the nomenclature from a third field. So this will be the last thing I do, I promise. So, why should this at all be related to nuclear norm, being good? Is remember the convex program we have. We have minimized the nuclear norm of X so that it agrees with their observations so far. So, the standard approach in statistical learning theory is to give some of these quantities names that we care about. So one is you can think about the empirical error. That's just of the things I've observed so far. For a hypothesis X, how close is it? Now the constraints of my convex program directly imply that the empirical error is always at most eta. You've always, whatever you output from this convex program is something that has low error on the things you've seen so far. But you don't really care about empirical error. What you care about is the true error. You care about in all of the entries, what's your average error? And what you care about is how much does having a good bound on the empirical error translate into a reasonable bound on the prediction error. That's actually a property of the norm. So there's actually a way that you can do this where what you do is, imagine this convex program outputs a norm 1 solution. So it has nuclear norm at most 1. Here's the crucial idea, which I'm going to say informally, is the main crux of statistical learning theory is that the way that you can bound the difference between the empirical error and the prediction error, what you've observed as the error and what the true error is is really, it depends on how well your hypothesis class agrees with a random function. So if your hypothesis class is so rich that it agrees with a random function, then the fact that you've observed low error on the observation so far is probably just an accident because you have too many hypotheses to begin with. Whereas if your hypothesis class is so constrained that it can't agree with a random hypothesis, then that means what you saw was not an accident and it's actually indicative of the true error going forward. So if you're actually asking how well you agree with a random function, that's actually literally case 2 now. Case 2, we put in random entries in the matrix, and we asked how well its spectral norm was. That's really asking for something with nuclear norm 1, so actually a rank 1 outer product, how well you can get it to agree with it. So actually the same spectral norm bound is what allows you to bound the Rademacher complexity. So in fact, the Rademacher complexity is exactly the same quantity that we've seen already, the same thing that allows you to solve the distinguishing problem, that allows you to solve strong refutation, and we already know what those bounds are, and the important thing is when that becomes smaller than the trivial bound, which is its Frobenius norm. So that is basically all I'm going to say. Now I'm going to wave my hands and tell you why most of the work for tensor completion is actually already contained in this. So the important thing was actually building a bridge and a dictionary between the two areas, because what I'm really saying is if you take refutation, you take matrix completion, there's an intersection point, which is this distinguishing problem. Now, and that gives you a way to sort of translate how two communities are doing the same thing. But once you have this bridge, you can do it for tensors too. That you can define the same type of distinguishing problem, approximately rank 1 tensor versus random. That's actually the same thing as trying to refute random 3 XOR now. So if you had amazing algorithms for tensor completion, you could ask what they could do for refuting random 3 XOR. And the truth is that they would do something way too good because they would allow you to refute things with n log n observations, which is bad. But if you had some mysterious algorithm for tensor completion that actually worked with n to the 3/2 observations, that would give you something that refutes random CSPs with n to the 3/2. The important thing is that that actually exists. Very recently, over the past few years, Koya-Oglin et al. Gave such an algorithm. And the amazing thing is you can actually take the bridge and traverse it in the wrong direction. You can take their algorithm, and what I was really saying was if you have a norm that works for tensor completion with n to the 3/2 observations, you could then refute random CSPs. But you can actually take the algorithm that they have and you can actually, it turns out that you can actually embed it within these hierarchies of STPs. That gives you a norm that does the same thing, actually gives you a norm with low Rademacher complexity, and that immediately implies how you can do for tensor completion. So there's actually basically no proofs in this paper, but it just follows from connecting the dots between things. So that's all I'm going to say is the quick summary. We had an n to the 3/2 times r algorithm, which actually completes tensors, for example, which non-trivially uses the interrelationships between the slices. In fact, it even works for highly overcomplete tensors, which we wouldn't know how to decompose if we had them entirely, which is bizarre. There's an inefficient algorithm based on the tensor nuclear norm. So there's actually a computational versus statistical gap here that when you look at the problems for linear inverse problems, we love to talk about compressed sensing and things beyond it, where it sounds like you can do everything, right? But the problems we're stuck on might exactly be cases where you can't do everything, and there actually is a non-trivial interaction between the two sides. So, the basic thing is, I think it's really exciting to try and explore computational versus statistical trade-offs through hierarchies and thinking about what complexity has to say about these problems, especially if the answer is not so pessimistic and that there actually are interesting algorithms, but that, you can't be unboundedly optimistic and always hope that you can do everything. So that's it. Thanks.
So just to return to your first example with this Netflix story, and when you talked last time about this two types of intelligence, you say that there was some kind of goal to achieve some explainable
Interpretable, yeah, yeah, yeah.
interpretable thing.
Yep.
And so, what was the outcome of this Netflix thing? So indeed, has a low rank. And you can somehow identify something with sport or.
Yep. So that's a very good question. So in the first, in the previous talk, interpretability was of the utmost importance because that also allowed us to say if there was a true thing, we could find just that and only that. Here, actually, the goal is just to get something with good prediction. So when you take the Netflix matrix and you decompose it, you don't get something which is, you get something which you can squint at and kind of interpret. But the important thing is that actually the nuclear norm minimization is one of the key things that allowed people to actually win the Netflix prize. Now, the truth is that Netflix put a goal for how much they wanted an improvement in the root mean squared error, where people very quickly got the lion's share of it with simple ideas. But at the end of the day, what took so long was the fact that people needed to assimilate many different ideas and create some classification system which incorporated 50 different signals. Nuclear norm was, I would say, arguably, the most important, or at least one of the most important. But there were all sorts of extra hacks in the system. Like, one of the hacks in there was you should also look at how far in the past people saw the movie that they're rating, because movies age differently in terms of how much people like them. So, for example, Memento, people love if they just saw it and then they don't like it. That had the largest negative slope, and Forrest Gump had the largest positive slope. And then there are also other quirks, like at some point someone realized that the movie Napoleon Dynamite, how much you like it has nothing to do with anything else about you. It's a completely unpredictable random variable, and that it contributes rank 1 just by itself because there's nothing to do with anything.
But is there then some kind of success story when something started with the decomposition and then people found a clear, understandable meaning of different rank 1 components or something like this? So it's one can believe that there is something really amazing in this direction. Did it really happen?
So this one, I think the main application of some of the nuclear norm things is just getting better prediction, not necessarily through interpretability. But there are other things that I've worked on where actually I have seen that phenomenon. So one thing I've worked on was topic modeling, where the goal is to take some collection of articles and actually create what are some notions of the underlying topics. So there's one particular data set that everyone uses because it's large, and it was done about 15 years ago, and it's called the UCI data collection. Now the point is that when we ran our algorithms and compared them to other people's algorithms, I was trying to look through the topics that it creates. Each topic is just a collection of words, and I was trying to understand whether it's a meaningful topic or it's a useless topic, right? And one of the things that I found cool was there was one thing that looked like noise to me, which had the words Cuba, Reno, Ilion, Raft. And then actually it turns out it's a real news story. So about 15 years ago, there was Ilion Gonzalez, who was a boy who was born on a raft on its way to the US. And the problem was that he was technically a US citizen, but they deported his parents, which I thought that was cool because it was barely at the limits of my knowledge of current events. So I had some vague recollection, and it was actually right when I was wrong. I thought it was a noisy topic because there are some noisy things in there. But when the noise actually becomes comparable to my own noise and knowing the news stories, I thought that was pretty neat. So there are examples from topic modeling where there are certain phenomena that they found. They also study things like how topics vary over time and have a periodicity. Things like the Olympics have a very high, really rigid periodicity, but they find other quirks that then later on sociologists can explain. So I'm less connected with this because I'm clearly more in the math-ish areas, but some of my collaborators actually work in things like the digital humanities, where they actually work with humanities people to actually leverage some of the statistical techniques and machine learning techniques to try and create, understanding, new phenomenon or identify new phenomenon. So people like David Mimno at Cornell and Dave Bly at Columbia. So not all the time. And yeah, and I'm not going to defend Spearman's hypothesis because I really disagree with it on a fundamental level. But
no, but maybe for more modest, if you have, I don't know, mathematical problems and students of the department, probably you can classify linear algebra and calculus.
Yeah.
They're somehow more clear.
Yeah.
Divisions, not. And another thing, so if you have a multivariate polynomial of small degree,
Yeah.
it's also somehow a tensor of
That's
low
right.
rank. So this reconstruction, the reconstruction problem of tensor of low rank, how it's related to error correcting in Reed-Muller codes or something like that.
Yeah, I mean, so the problem is that knowledge about tensors is spread across many different communities, and the same way that, you know, as you're saying, a tensor is you know, multilinear polynomial of some particular fixed, you know, homogeneous degree. It's also spread across like quantum information theory. Each one, it's kind of difficult. Like they give very different kinds of insights. So actually, you know what? Maybe I'm going to take that question offline, so I can say more about that. That's a bit technical.
So you were saying, yeah, can we take it offline? Okay, so let's thank Ankur again and take the remaining.